Wait. Oh. No.
Okay,
Too
okay.
late.
Yeah.
was
Welcome
gonna-
to the AI Show. I'm Scott Stephenson, co-founder of Deepgram. With me is Jeff Ward, a.k.a. Susan.
Hi, all.
He's a Navy pilot, acclaimed dad joke writer, and AI scientist at Deepgram. On the AI Show, we talk about all things AI. What is it? What can you do with it? How does it affect you? Where is it going? We are live and ready to answer your questions. Comment on YouTube and Twitch or tweet at Deepgram AI to join in. Today, we're asking a couple big questions. What are those big questions? What are the different types of machine learning? That's one. And what are the different types of data? So what do you think about number one?
What are the different types of machine learning? Well, that's a huge area. Why don't we just talk about one for right now? Reinforcement learning, right? That's near and dear to my heart. I love reinforcement learning.
But usually people think about like three different types, right? Like a reinforcement learning, unsupervised, or supervised, right? So yeah.
Well,
you can get into slicing this up however you want, but yeah.
Yeah, we'll get into this a bit in the future, but unsupervised, supervised,
what's reinforced
learning? Reinforcement learning is learning from a series of actions where you get rewards along the way, or series of choices where you get rewards along the way. So, a classic one that's been in the news is AlphaGo. That's, a large chunk of reinforcement learning techniques are used in there. Specifically Monte Carlo tree search techniques. A lot of other ones. One that's been getting a lot of press lately.
So AlphaGo is people play the game Go,
playing the game
right?
Go,
But
yes.
this is a machine playing the game
Yes.
Go and being very good at it, beating the world's top Go players.
But another one that's really fun and has popped up in the last couple of years is based off of Atari games. And Atari specifically is a great toolkit. If you're into this world, if you want to learn more, dig up the Atari learning environment and start going through a lot of code associated with that.
Is this something OpenAI did, or is this some other thing?
Oh, who built the Atari learning environment? I forgot the group that started it off. But it's a phenomenal toolkit for all sorts of stuff, but specifically it's been helping reinforcement learning. Because these games, a lot of them are a series of actions. They lead to a reward, a score. It fits the metaphor perfectly, and it stretches it a bit. Because
What's the metaphor?
Well, it fits the series of actions leading to a reward, right?
So reinforcement learning is like, hey, I'm taking some actions. I can do any number of things, but what I'm trying to do is make some number go up, like my score or my happiness or something like that.
Exactly. And classically, there isn't necessarily just one reward at the end. You can get rewards along the way. And the question is, how do I maximize that in the infinite game, right? How do I get the biggest payoff throughout time? And so it's great. It's great because it allows you to not only explore classic reinforcement learning, but also get into things like image recognition. How do I look at the screen? What does it mean to do that? Also, what parts of that screen are important? What do I focus on? There's a lot of great techniques that can draw you in there. You can do simple stuff, really complex stuff. It is just a fun, awesome environment to explore. Nothing but a bunch of great technologies.
But in like short terms, what is reinforcement learning like good at? What kind of problem would you throw at reinforcement learning and say like Go and you'd expect it to work?
So reinforcement learning has a lot of problems that fit into graphs, right? So a series of actions that lead to other choices, actions that lead to other choices, actions that lead to other choices. So map, trying to find a good path on a map, trying to win a game, one of the 1,000 Atari games out there, trying to play a game like checkers or chess. That classic one, I take a move, my opponent takes a move. I take a move, my opponent takes a move.
Yeah, where things are pretty rigid, the actions that you take are known. There aren't things that are like an act of God is going to come in and change something. Here's your environment, play in it.
Our current best is basically where there's some basically finite set of states, and they transition in some way that we can model, and they have actions that help us that affect those transitions. So say I have 4 options in front of me. I choose A, and I'm in state in right now. There's some probability based off of the action I choose for what state I'll end up in after that. And this reinforcement learning allows me to understand those probabilities, those transitions, and also what's called the best policy. In other words, given all this information, what is the best action I should take to get some sort of, reward in the end. It sounds dry and academic when you start talking that way. It's a lot better when you say, hey, I'm going to play pole position, and do I move the car left? Do I move it right? Do I tell it to speed up? Do I tell it to slow down? It's the same thing, and then based off
and it might have access to the image,
Yeah.
right? It can look around. It could look on the screen. It can see if a car has passed it or not, but it has to figure all those things out on its own. But still, it's getting the input from the screen. It knows what position it's in, and it's trying to make that position number one or make its lap time faster.
Exactly.
In the game.
So it's great because when you're in, again, going back to the Atari learning environment, when you're trying to frame this as a reinforcement learning problem, you've got to figure out how to identify the state you're in and what actions are available and do those different things. And there's been a lot of work trying to make this more unified, so to speak. So have a generic program that can play multiple games, right? Based off of this input.
Just an ultimate gamer.
The ultimate gamer. And also, this is leading to a lot of really, really deep, interesting research questions. Like, some games are basically just reflex based. Where it's like, hey, the bullet's coming towards me, I go left. Whereas something like, say, Pitfall Harry is not exactly a reflex based game.
What's Pitfall Harry?
Oh, I'm showing my age here. Pitfall Harry is basically the most awesome Atari game ever.
All right.
Tell
me more.
You're on a quest through a jungle, and you've got to jump over water hazards,
So you
and
have like a
swing
vine.
on vines, and avoid the alligators, and
Got it.
and find all the things that are throughout this maze of screens to win the game. It takes more than just a simple understanding of bad guy there, aim and shoot, or go left or go right.
Because you have to like switch some switches or something. You have to go back through different screens. You have to remember what happened before.
Yeah, and also just the way you analyze the screen is different depending on where you're at, what you're looking at. It's a much more complex problem, and it shows the some of the limits of some of our simple ways of thinking about things.
It's not necessarily like just shoot the red ball or something.
Exactly.
That would be very easy for a reinforcement learning algorithm to figure out. Okay, just keep shooting at things that are red and go to town. Red and round. So
again, this is a wonderful environment for exploring a huge, rich set of problems. At multiple levels here. I really encourage anyone to check this out and play around with stuff that's out there.
What do you think about unsupervised learning?
So when we talk about unsupervised, supervised, semi-supervised, the classic definitions are all around data. So supervised learning, you've got a bunch of labeled training data. It's all labeled.
What does labeled mean?
Labeled meaning like I've got a picture of a cat, and I've got right next to it cat.
Yep.
I got a picture of a dog, and right next to it's a dog. I got a picture of a muffin, and right next to it says muffin.
Yep.
Right? All of these, every single piece of information I've got has the answer of what it is right next to it. And from that, one of the most famous that people start off with is like the MNIST handwriting digit recognition. I've got the answer. This is a 1, and you've got all these.
So these
things.
are images where people have written numbers on a piece of paper. So they handwritten digits, and that means 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, right? And many different people have written many different digits, but they've all been labeled. So somebody has gone through and said like a 1 is a 1, and a 5 is a 5, and an 8 is an 8, and it's collections of I think 28 by 28 pixels.
Sounds about right.
Yeah, 28 by 28 pixels, and this was done in the late 90s essentially.
Yeah.
But it's a large number. I think it's 60,000 images.
Yeah.
And there's a whole bunch of them essentially. But yeah, it's just black and white images of 28 by 28 pixels. But you can read it. You can look at it as a human and be like, yep, that's a 2.
And it's great as an academic set, and it was also very useful when it came out for practical things like reading the mail and stuff of that nature. But it's great.
Yeah, this is, I think, actually implemented in the post office in in late 90s.
Yeah, so it's awesome because it's small enough from a data perspective that pretty much anybody with their home computer can do real networks against it and see real real results. and apply some basic stuff and have a good time learning a lot of stuff about it. It's also very easy for you to pop it up. Oh, that's a 1, that's a 2, or you know, whatever, and kind of see where your
yeah,
model
you only have to
messes
pick
up.
from 10. It's not that hard, right?
Yeah.
You know,
Not a
but
lot
there are
to-
many different objects in the world, right? Like for other data sets, like
So
ImageNet.
ImageNet, CFAR,
CFAR,
that's one of
yeah.
my favorites. 10 and 100 there. That one's actually great because CIFAR. That one's great because you can start off with the simpler world, the 10, and then go to
So
the
they have it's the same images, right? It's a large number of images. Again, they're color images, but it's the same ones, but they're labeled differently. They're either labeled into 10 categories or 100 categories.
I forgot whether it was whether they were different data or not, but they're
Pretty
exactly
sure
the
they're
same format,
Yeah,
right? Yeah. So the same number of pixels and colors and all that stuff. So you can use basically the same model.
Yeah, so you can take the same data and say like, okay, I'm going to try for the simple thing, just picking from 1 of 10, which would I think it's like airplane, car,
that kind of simple
animal,
stuff,
you know, things like that. And then maybe the animal would have 10 different ones where it's like dog, cat, you know, lizard, whatever.
Yeah.
I don't know exactly what they are, but yeah.
But that's another great like kind of step up because you've got more data to play with, a harder classification task to deal with. The simple model that, you know, a simple 2-layer feed forward network that would have worked on MNIST will not do nearly as well on CFAR. So it allows you to kind of step up your game that little bit. But both of these sets, which are fully supervised, you know, you've got the answer sitting in front of you, are also, how to put this, they're not super realistic in the real world. You know, they're well cropped. You know, things are well sized. Everything's exactly the same dimensions. Which is great for learning, but the real world has a lot more problems than that.
Not all images are the same size or zoomed into the same level,
exactly,
etc.
Yeah.
But yeah, but to touch on the
world.
supervised versus unsupervised more though, you could use those data sets even though they are supervised data sets. They do have labels. You could use them in an unsupervised way. You just wouldn't use the labels then. Right.
Yeah. So that goes the other end, unsupervised. You have no labels, and then how do I start learning this stuff? We'll talk about the middle ground, which is semi-supervised. So semi-supervised says I have some of the labels, right? And I'm going to use unlabeled data to help me boost my results in some way. You know, think of this as audio normalization. This could be an example of semi-supervised. I got a bunch of audio, and I'm just going to use that to help me normalize background. But I'm really only learning on the subset that I have.
I mean, like the volume?
Yeah, like the volume or something
turning
like
up the
that.
volume,
You know,
or
some
trying to
simple
reduce
stuff,
noise or
some
something.
simple stuff like that, right? Or I could use it in more complex ways, like, you know, using it to learn how to compress down and then try to, you know, rebuild the exact same audio stream.
So to expand on that some more, it's like, hey, if I gave a network or some machine learning algorithm, if I just gave it the original image, right, and then I force that network to squish down into a really small space, meaning it can only hang on to a few numbers, essentially, but then it has to rebuild that and then try to come up with the original image. If you squeeze that down into like one number, you know, it can't reconstruct any image then, basically, right? It could just probably do like how bright or dark it was or something, right? But you expand that out to a few numbers, at least now it can start to construct like what color the image was and maybe some shapes in it and expand it a little further, etc. Then now it kind of looks like the original image, essentially, but it's been compressed way down, so it's not the same size as the original image. So this is like a traditional unsupervised technique. And then what you do is you take that model that tried to squish it down and you use that later.
Because
in a supervised way or something.
Because you know, basically what that last little bit is that little squished down version is the essential information behind that image, right?
Yeah.
So it's a great
Yeah, so like
way.
I see circles here, it's red, you know, I see some texture here, like maybe it's like feathers or something. It doesn't even know the idea of feathers, but it knows that it's sort of grouped together, and then you can use that information later.
Yeah, so there's all sorts of things, and this is where just the word semi-supervised comes into play. Every single problem, you're going to find some different way of using unlabeled data to help you out.
Yeah.
And there isn't this is the set way of doing semi-supervised learning. It's this, I found this great semi-supervised technique to help me out in my problem X. And in general, that's the way it goes. Supervised world, there's a lot more canned answers. Semi-supervised, a lot less canned answers. unsupervised, it's pretty hard to find answers.
Yep. But as we move along the conversation, though, we sort of started out with the more academic side, like the reinforcement learning. Is that super useful in real world today, like business or something? Not so much, right? You could dream up ways, but is that what people are running right now in order to like save money or whatever? That's not what they're doing in their business. They're probably using some sort of supervised learning technique.
Yeah, the majority of what we're thinking about in the machine learning world is, supervised, likely a deep learning, world.
So this would be like translation, going from English to French or something like that, doing speech recognition, going from an audio recording to the text that was spoken, etc. Those are all trained. They might be augmented a little bit with some unsupervised technique, but it's almost 100% supervised.
Yeah, well, currently. And this is where, again, as we move forward in this world, like the real future is semi-supervised, unsupervised, whereas as much as possible, because that's where most of our data lies.
Well, that's how a human learns.
Yeah, exactly.
Yeah, at
humans,
least semi-supervised.
We bootstrap.
We test the world. We poke.
Exactly. Mom and dad start off by saying apple.
Yeah.
Apple, and then later on, you start testing the world by saying apple.
Yep.
Right? And then you've got a
it
shoe
works
in your
out.
hands,
But then you hear
right?
somebody with an accent that says apple, and then you can kind of work out from context. They must mean apple, and I'm going to adjust my acoustic model.
Yeah. We start learning more and more and more with, unlabeled just by going through the world. And that's really an amazing thing that we need to learn a lot more in obviously the machine learning world. Like the more we can get those techniques and rip them out of our own head, so to speak, the more we'll be able to take advantage of the huge data sources that are out there.
Yeah. Yeah, but I still think from a pragmatic perspective, like, hey, you're a business and you want to tackle some problem using machine learning. You don't start with unsupervised.
No.
You don't start with reinforcement learning. You start with supervised learning. You go and label some data. You go gather data, then you label some of it, and then you train a model and see how well it works. You probably don't even start with deep learning. You start with some tree-based method or something like that.
Yeah, but you definitely have to have data. First of all, if you don't understand your problem enough to kind of have a data set of examples and answers, then you definitely don't understand the problem well enough to train something to figure it out.
Yeah.
Right. So
it brings us to our next question, right? What are the different types of data? What do you do with it, etc.?
Oh man, what are the different kinds of?
You can start high level though, right?
Like, like image and audio.
String
text.
A bunch of images together. Now you've got a video.
Yeah, sequences in general. We've talked about sequences before.
Yep. But it might be like I turned right down this street, I drove this long, I turned left down that street, and Google's trying to figure out what your intentions are. Are you going to a restaurant? Are you, should I pop up a gas station? Things like that.
Yeah,
all of these things, like a sequential set of events, okay, now what? Or I clicked on this thing on a website, then I clicked here, then I clicked here. Which ad should I show you? Or what should I suggest to you? Or something like that.
Which, by the way, are great examples of where reinforcement learning is winning big.
Yeah.
But again, on the big classes of data, we're definitely blurring what it means to say classes of data anymore. Like, sure. It's easy to say this is an image, this is video, this is audio, this is whatever. But now we're trying to fuse together a whole lot of different sources of data to help us answer the question at hand. Make the money. What information sources do you need? Is it clicks? Mm-hmm. Is it pictures? Is it audio? Mm-hmm. Is it text? Is it bank accounts?
Yeah.
Is it all these different sources of information.
Yes, usually called multi-channel in like a business setting, right? Where maybe somebody emails you, they send you some chats, they also call you on the phone or something, and you're trying to fuse all that information together, build a model, and predict something about them. Like, are they pissed off? Are they happy? Are they whatever?
And that's a big challenge on two fronts. First of all, we've got a lot of great techniques that are sifting signal from noise, but the more noise you give it, the harder it is to work. And sometimes adding more data actually hurts you. So if you can filter out a lot of bad sources, you're going to probably make your model better. Focus on useful data that has predictive power. It's not. There's this common misconception. If I just put enough layers, enough neurons together, and enough data sources, and then run it for a long enough time on a big GPU, magic and the right answer happens on the other end.
Yeah.
And
Not necessarily the case.
That is almost never the
Yeah.
case.
Yeah, there are other constraints that come into play.
Yeah, I mean, just purely dealing with that data becomes a problem, but
Yeah.
also just, more data means a longer time before your model converges, before it starts being able to give predictive power. And sometimes it's so far that it just never gets there, right?
Yeah. So you're saying don't get data?
I'm not saying don't get data. I'm saying try to figure out how
much
useful
you
your,
need.
your data
Yeah.
is. What, if you can pre-process it, you might make a huge difference on your model in some way,
Yeah.
Just, we'll talk audio for a second. If you do absolutely nothing in your audio and send it to a model, you probably will get better results for whatever you're doing in that audio if you normalize it. You kind of smooth the highs and lows and get it back into a normal range. It's all about getting to a baseline, because in general, a lot of our techniques, what they're really good at is saying, hey, given that something's at this baseline, I can tell you nudge it up this way or nudge it down that way. But if the data's coming in down here all the
you gotta
time,
shift the baseline
it's got it working really hard just to predict up to the baseline and go above
Yeah.
it, and it's going to be biased in some way. So if you can get it through some simple statistical technique or whatever to a reasonable baseline, it's a lot easier for your model to nudge it in the right direction and get the right answer.
But to give some scale, essentially, like what is a large image data set, right? Hey, MNIST was like 60,000 images. That's not generally considered like a large image data set. It's pretty big. It's good. It's good for what it's trying to do, right? It can tell handwritten digits pretty well. But the large data sets in the world, like ImageNet, which is actually, it's not 10 categories, it's not 100 like CFAR, it's 1,000 categories, and I think it's 19 million images or what are labeled into those categories essentially. And that's a pretty big data set, but is it the biggest data set in the world?
Close.
Like, no.
And it's also purely just academic right now. Like, what's going on in the world, especially when you look in the self-driving car world, is the visual information that they're sucking in, the terabytes worth of data that they're processing through their models make just 19 million images seem quaint. It's just like they're sucking down large portions of YouTube, that kind of stuff to
well, and they also need data that's a lot that's like segmented, right?
Oh,
and
yeah,
so
it's
not
hard.
just, is there a cat in this image? It's like, there are 3 people in this image, and I've drawn the outline of the person, I've drawn the shape of the road, and I've drawn like the traffic light and things like that, so it knows exactly where it is. And
which actually, not to give plugs here, but NVIDIA and their synthetic environments, that's a really great thing, because effectively the true answer.
Simulate it, like just play Grand Theft Auto 5, but it's there.
And we've been doing this for a very long time, trying to make incredibly realistic environments. So computers are able to learn from all of those years of work of making really good video games and movies. You can do things like maybe get a good chance of learning how to drive a car or something like that. That synthetic augmented data is a big range of data that's very important to our data world.
So you kind of have to think about your task, right? If you're choosing from one of 10 categories, then maybe like 60,000 or 10,000 or 100,000 or somewhere in that range is like the number of labeled piece of data that you would need. If you're choosing from 100, 100 categories, maybe, it's 5 or 10 times that. If you're choosing from 1,000 categories, maybe it's another 5 or 10 times that in order to get up to the amount of data that you need to tell the differentiation between them. But in the speech world, maybe this isn't, we're not talking images anymore, right? We're talking about like maybe hours of labeled audio or seconds of labeled audio, right?
Yeah, that's an interesting one. Obviously,
Deepgram does speech. That's all we do. So that's what we think about all day.
We do think about it all day, and speech in general is a really, really interesting world, because we were talking about this earlier. How long does it take a human to learn? How many hours of audio does it take for a human to learn a language, even from infancy? And
to get a really good grasp on like your one language that you learn from birth, it takes probably like 10 years.
But when you think about the amount of audio that was heard, that was really not a tremendous amount. So
Yeah, maybe tens of thousands of
maybe
hours
tens of
or
thousands.
something like that of speech that you've heard and in a semi-supervised way.
Exactly, in a
sort
very
of-
semi-supervised
very
way.
semi-supervised way.
And the crazy thing is, our models, training a world-class speech model generally takes a lot more than that. And so
yeah, you're talking tens of thousands of hours, or maybe 10 times that.
Yeah,
you know, yeah. So
to really help you out, getting all that varied. So what is it about?
and it's all purely supervised as well,
Yes.
right? So a human is semi-supervised at about 10,000 hours. It can like master a language, but a machine at 10,000 hours, even supervised, not really master the language. It's doing pretty well, but it's not mastered, right? Maybe 10x that. Now you're getting to the territory where it feels like it mastered the language, but still, it was a supervised way, not a semi-supervised way.
So how, what is it? What are the mechanisms that allow a human to do that? That we don't have available to us? Is it how we're representing the information? Is it the structure of the model inside? Are we asking the question the right way?
Oh yeah.
These are, this is where speech is such a fun area, because there's clearly examples where there are learning algorithms of the world.
Yeah.
What's in your head that beat the living daylights of what's available on the computer side, and that means there's a lot of great fun play to figure stuff out at.
Well, some of it's just like tone, inflection, things like that, but it's also just like you understand the world around you. You know when somebody says, frogs make the best wine, right?
They do.
The frogs aren't making
they don't
the
have
wine,
enough sugar in their blood, right?
Yeah. But is it that the frogs are making the wine, or is it that you turn frogs into wine, et cetera, right? And like, how does that go, and what is the first thing you think of? Or, I couldn't put the pineapple in the suitcase because it was too small. What does it refer to? Is it that the pineapple was too small, or that the suitcase was too small? We can figure that out really quickly, we know. Mm-hmm. But machines, it's kind of like, huh? Yeah.
Yeah, I saw Grandma with a handsaw or a power one.
What was the saw here?
I mean,
there's a lot of common sense here.
Yeah,
that
there is.
Humans are able to apply really easily.
There is, and
another really large data set is text, though.
Oh, text, yes.
Text is huge.
It's huge, and it's awesome.
The web exists. There's tons of textual data all over the place, and titles and bodies of blogs and just everywhere, right?
And the great thing about text is you can learn so much in so many different fields. It's not just, we're going to only apply this to translation or only to transcription. Mm-hmm. You can start using text to start learning about some subject matter, and helping your model in interesting ways with that. Like, text is a great secondary source to so many problems out there.
Yeah.
If you could figure out how to work it in, just because there's so much, and it can be compactly represented comparatively to things, And images,
text is like the biggest, richest data source that people have right now, just because the internet exists and everything is kind of in text.
Yeah.
Video is kind of growing, audio is growing, et cetera. Images are growing, but text is massive.
Yeah, and a picture's worth 1,000 words, maybe even a bit more. 1,000 words may be worth more than a single picture, in all honesty.
Yeah.
And how much meaning it conveys.
Yep.
There's a lot of great stuff in text. Oh man, yeah. So huge things. The synthetic world just is a big, broad category. Synthetic versus truly labeled. Supervised data versus unsupervised.
We didn't even talk about how you get the labels, right? Humans do it. You have a bunch of humans that look at images and say that is a cat, or they circle the person and say that's a person, or they listen to audio and they type out what was said. So it's a very, very tough work.
If there's a lot of people and companies that think, hey, I can do that. And maybe you can build the model. Maybe you can buy the GPUs. Maybe you can set up the servers. Yeah. Maybe you can dedicate some people. But just go out and find the data.
Yeah.
And pay either pay the millions of dollars to find to get it, or the tens of thousands of man hours to
right now it's not easy
hours to do it.
There isn't just here's a $10 million check and get a data set labeled. It's more like you're going to be waiting 2 years or a year or half a year or whatever it is, and you're going to be orchestrating the effort. You have to do it.
Management challenge.
Yeah.
Getting that data is.
I mean, there are certain companies that help with that, right? Yeah. That will label images or label text or whatever, or label audio.
Yeah. Or whatever, gather whatever data. Just think about the data it takes to go out and build a map in the world. Physically getting people out there. Data is that data be useful not only today in the problem you've got, but probably 10, 20, 50 years from now.
Yep. Well, I think we covered the areas pretty well here. What are the different types of machine learning? Reinforcement learning, unsupervised, supervised. We talked about data. How do you get it? What is it? What's a good scale, right? Mm-hmm. So that's it for us today. Thanks for joining us on the AI show. What questions do you have about AI? Comment on YouTube or Twitch, or tweet us at Deepgram AI. We're Scott and Susan from Deepgram. We come in peace.
Hopefully.
Yeah, we're certainly not robots. See you next time.